Recording. Okay, so today we're gonna talk about chapter 13, which is wild stuff. Like this is very almost like this title is a misrepresentation. What the heck we're gonna talk about? Um, and I think we should be wise in terms of the exercises we should do because there's so many of them, right? And I'm gonna let that responsibility, you guys be responsible for that. So which exercise we should focus on? Okay, so the chapter starts by saying that some great stuff comes from very unexpected places, and that's definitely going to be the case right here. Because we're going to start by throwing a very questionable definition here, right? That at first I have no idea how somebody came to this idea. I understand that this is going to have wild consequences, but if you don't know the consequence first, how you're going to come up with, oh, what happens if I fix a guy and I apply the operation on the subgroup of a group for all of the members of such subgroup? What happens? Like, how do you come to that realization, really? But okay. Let G be a group and H a subgroup of G. For any element A in G, the element AH denotes a set of all products AH as A remains fixed and AH ranges over H. AH is called the left coset of H in G. Uh, yeah, and so we're gonna essentially apply the operation with this on the subgroup, fixing the A, but it's important to remember that A is any element of G, of the like bigger group, right? And if you swap the order around, you have a right coset instead of a left one. For the remaining of this chapter, we're gonna refer to cosets as right cosets, just for convenience. So okay, we have this, what seems to be like a silly definition at first. And we say, okay, what can we do with this thing? When we deal with cosets in group G, we must keep in mind that every coset in G is a subset of G, obviously. Thus, when we need to prove that two cosets HA and HB are equal, we must show that they are equal sets. Makes sense. What this means, of course, is that every element X that is contained in HA is in HB, and conversely, vice versa. For example, let us prove the following elementary fact: that if there is an A which happens to be in HB, then HA equals to HB. We are given that A is in HB, which means that if you that there will be an element A that can be described between the right coset H1b for some H1 in H. We need to prove that HA equals to HB. So we know that X is in HA, right? This means that we can describe X in those terms with an H2A, H2 being in H. But we also know that A from above is equal to H1B. So when we say that X equals to H2A, we can swap the A. We can swap the A, yes, with H1B. And then if you use associativity, you get this thing. And the latter is clearly in HB. And that is a question. No, this is not a question that I have. We know that this is in H because of the definition of the subgroup, right? That's why.
Uh, yes, but also because, well, it is in part because of the definition of the subgroup. For it to be a subgroup, the identity element has to be in there, right?
Yeah, but how do you know that H2 operation with H1 is in H? It's because of how subgroups work, right? Both of them came from
Yes,
H,
Yeah,
because
from H, and by the definition of the subgroup, if you apply operations on any two elements with the operation, you're going to still be in H.
yeah,
Cool. So this proves, because remember, this latter part is X. So this proves that every x that is in HA, which is the premise, is also in HB. And analogously, you can do the vice versa to prove with a y in HB and do the same exact process, and we're going to have that HA is equal to HB, just for the simple fact that the fixed guy is in the other guy, right? So that's not that surprising, I would say. And then we go to our first theorem, which starts like wiring everything up. Like we saw partitions and equivalence relations. Those are going to matter right here. The family of all the cosets HA as it ranges over G is a partition of G. Boom. First, we must show. Okay, again, remember, just a reminder. What is a partition? The partitions are the things that they are disjoint, and the union of them is equal to the group, right? That's what they are. So let's say we must show that any two cosets, say HA and HB, are either disjoint or equal, which is very convenient because that's kind of how we prove the partitions. If they are disjoint, we are done. If not, we say that X is within the intersection of them. Because X is in HA, say like that, for some H1 in H, because X is in HB, we can say that it's also described like this for some H2 in H. Thus, we say that that X is equal to X, so these two things must be the same. And solving for A, we have this thing. So this is probably just doing some manipulation, right? Because you can divide this thing and then use the inverse, and you're going to have this thing. And we know by the definition of the subgroup that this is in H. So A is equal to HB. Well, A is in HB. We can say that. We follow some property 1 that HA is equal to HB. So what we just proved is that either HA and HB are disjoint or equal. Half of it is done because if they are disjoint, we are done. We just have to prove that they would be equal otherwise. Next, we must show that every element C in G is in one of the cosets of H, which is easy because you can describe any element by applying to the neutral element, which of course is in H. And therefore, we can say that any element could be described in terms of a coset. That was very, even for me, that was easy. Come on. Thus, the family of all the cosets of H is a partition of G. Cool. Um, okay, there is a small comment in here. A given coset, say HB, may be written in more than one way. By property 1, if A is in any element in HB, then HB is the same as HA. We've seen this before. Thus, for example, if a coset of H contains n different elements, such as these ones, it may be written in n different ways, namely these ways. The next important fact about cosets concerns finite groups. Let G be a finite group and H a subgroup of G. We will show that all the cosets of H have the same number of elements. This fact is a consequence of the next theorem. If HA is any coset of H, there is a one-to-one correspondence from H to HA. This is also very intuitive to me because if you swap the fixed member, but you keep the subgroup thing, of course there will be a one-to-one correspondence, right? Because you're essentially multiplying a constant with everybody. So that kind of follows. But we have to prove it, so let's go. The most obvious functions from H to H. A is the one in which from every H in H matches H with HA, of course. So we have a function like this that can be defined by just multiplying the constant. Easy. Now, is F bijective? That's the question. Well, to prove that it's injective, we have to prove that they are mapping to unique things, right? If F being applied to F gives you the same image, you are the same domain, and that's exactly what is written here. So if this is true, then this is true, and therefore this must be true. So everybody will be different. like if the values of the domain are different, the images will be different. And next, if it's surjective, because every element of HA is in this form for some H and H, and the F just does the multiplication, thus there is a one-to-one correspondence from H to HA, as claimed. So okay, so cool. By theorem 2, any coset HA has the same number of elements as H, and therefore all the cosets have the same number of elements. Which again, this seems, all of this so far seems very like fine, right? Nothing crazy. The craziness is about to come though. Just wait a bit. Uh, so what have we seen so far? Let's take a look carefully. Let G be a finite group and H any subgroup of G. G has been partitioned into cosets of H, and all the cosets of H have the same number of elements, which is the same as the number of elements in H. So good so far. So good. So far so good. Thus, the number of elements in G is equal to the number of elements in H multiplied by the number of distinct cosets of H. This is the beginning of something special, right? Because now we can talk about the number of elements of the bigger guy in terms of the number of members of the smaller guy. And this is where it starts to get a little impressive, right? Because usually if you have a bigger thing and you have to talk about something contained in a bigger thing, that's kind of obvious. But this is kind of going the other way around. We're going to go there, which is you have the smaller guy, and you want to talk about the bigger guy. So it's kind of impressive that you can do that. And this statement here is just a way of stating the Lagrange's theorem, apparently. So let G be a finite group and H any subgroup of G. The order of G is a multiple of the order of H. Okay, in other words, the order of any subgroup of a group G is a divisor of the order of G. And again, order is the number of elements, okay? So I forgot to put this to say that, but we know that, right? So for example, if G has 15 elements, its proper subgroups may have either 3 or 5. If G has 7 elements, it has no proper subgroups. For 7 has no factors other than 1 and 7. And then this starts the number theory stuff, right? This is again very strong connections to number theory stuff. Let G be a group with a prime number p of elements. If A is in G and A is not the neutral element, then the order of A is some integer different than 1. But then the cyclic group A has m elements. By Lagrange's theorem, m must be a factor of p. But p is a prime number, and therefore m must be equal to p. It follows that the cyclic group A has p elements, and it's therefore all of G. And then I have a question because I haven't, this is already like accumulated a bunch of stuff. This notation is just to say that this group is cyclic, right? There's nothing really
It's cyclic with A as the generator, yes.
Okay. So theorem 4, if G is a group with a prime number of number p of elements, then G is a cyclic group. Like wild stuff, right? Just by how many elements the group has, you can already say there's a cycle in there. Wild, no? You don't even know the function, right? You don't even know the function the group uses. And you can say for sure because there are a prime number of elements, there is a cycle in there. Wild, man. Wild stuff. And furthermore, any element which is not the neutral element in G is a generator of G, which is also wild. So what it says is that there is, up to isomorphism, only one group of any given prime order P. For example, the only group up to isomorphism of order 7 is modulo 7 in integers. The only group of order 11 is modulo 11, and so on. So we now have a complete information about all the groups whose order is a prime number. Wild stuff. By the way, if A is any element of a group G, the order of A is the same as the order of the second subgroup A. And by Lagrange's theorem, this number is a divisor of the order of G. Thus, the order of any element of a finite group divides the order of a group. Can somebody remind me what does it mean to say the order of an element?
Which is the lowest positive power of that element that is equal to identity.
Ah, okay. Yeah, that is again modulo stuff.
Yeah.
Okay, so finally, if G is a group and H is a subgroup of G, the index of H in G is the number of cosets of H in G. So this is new naming, nomenclature, right? So index. So index of H in G is the number of cosets of H in G. Okay, so these are the number of partitions.
Basically, yes.
We denote it by this syntax. Since the number of elements in G is equal to the number of elements in H, multiplied by the number of cosets of of H in G, so we get the order of G divided by the order of H. This is going to be the multiplier factor, right? This is what we're going to be multiplying one to get the other. And that is the index.
Essentially, yes.
Okay, so wild stuff, no? Like, am I the only one impressed by this?
Well, in some sense, this is inevitable.
Oh, but what do you mean? What do you mean?
uh, well, it's a theorem, right?
I don't
But
understand. I still don't understand what you mean.
okay, let's put it this way. It is impressive, yes, but it's also inevitable
No,
because it follows from the definitions given, but
yeah,
it's not obvious, is the thing.
yeah. I don't understand your second portion of the statement because every truth that is yet to be discovered is gonna be like inevitable, and they are still impressive. Like something being inevitable doesn't move the impressive metric to me at all. Because if they are truth, they would be inevitable anyway. So like every theorem, like well, anyway, you agree. I agree with the first portion. It is pretty impressive. And again, we can talk about so much about these things, and again, with no regard of some details that you would think matters. For example, like I said, to say that something is cyclic, the first thing that I want to know is what is the function. But I don't need the function if I know how many elements are there. Crazy. Okay, and now the exercises. And like I said, we have 42 minutes, and we have many exercises in this section. And I will let you both of you guys dictate which exercises we should do. We should focus on.
Hmm.
So exercise A. I think the only remarkable thing that I would like to talk about on this one is the example, right? Because just to have a taste on what the heck we mean. So if you have modulo 4 as the G group and you have the subgroup of the member 0, 2, it wants us to list the cosets of H in this situation. And the only ones that you can do is pinning the A to 0 and pinning the A to 3. And the reason why is because if you pick any other one, you're going to get the same sets anyway. So if you do H plus 2 and you apply that to the members of H, you're going to get 0 and 2. And with 1, you're going to get 1 and 3. Every other possibility of A, which in this case would be 2 and 3, you're going to get 2, 0, and 3, 1. But because these are sets, it doesn't matter, right?
Yeah, this goes back to what we were saying earlier about cycles, right? Um, in this case, because you are using a subgroup of order 2 and the group it belongs to has order 4, like 2 is a factor of 4, so you actually can't cover the entire domain, which means if you use a coset, then you can get to things that are outside of that and that are different, right? Um,
Mm-hmm. Okay.
Which I
Any.
figure might be one of the ways in which people arrived at the notion of a coset anyway, in the first place. Like trying to generalize partitions in this manner, cycles
Well,
and partitions.
yeah, but the definition of a coset has nothing to do with both of these things, Tiv.
Kind of has if you squint. Like, I can see how you could go from a concrete example of a cyclic group to the definition of the coset. But of course, I can't say for sure that's what actually
Well, I mean,
led to the discovery of
if you
that.
know where you wanna go from, like where you wanna go, what is the target? Maybe you can, but like just reading this, nothing here is mentioning cycles or modulo or whatever. This is literally just multiplying by a constant.
Uh, you could say it's also adding the other portions of the cycle. So like you have a cycle if you have like Z6, you are going to have 0 and 3 and 0 and 3, but then you can also add the other elements to get 1 and 4 and 2 and 5, and that kind of seems like generalizing that, but maybe it's hindsight, yes.
Maybe. I can give you the maybe. I can give you that one. Okay, any further comments on A?
not really.
Okay, any comments on B?
Cosets in infinite groups. Can I just say that, like, and B7 in particular is a bit dubious because you're asking for a division between two infinities and getting an integer like value out of that.
Well, but that depends if the infinities are countable or not. But well, I don't want to go in that discussion today. Let's talk about B1, just to have a very simple case.
Describe the cosets of the subgroups. In this case, the cyclic subgroup of 3 in Z.
What is the cyclic subgroup of 3 again? Is it modulo 3?
It's all of
No,
the multiples of 3 in
All
both
it's all.
multiples, yeah,
directions.
yeah, I remember that.
Yeah, basically, given the element 3 and its inverse, what are all the possible combinations? In this case, since the base group is Z, the integer group, the operation is addition, so it's like 3, 6, 9 in the positive direction, and also -3, -6, and so on in the negative direction. So yeah, it's all the multiples of 3.
Okay.
And the cosets of that are basically like the multiples of 3, the multiples of 3 plus 1, and then the multiples of 3 plus 2. So
Yeah, because of anything else you're gonna be repeating yourself, right?
yeah.
Yeah. Yeah, yeah, yeah. Okay. Cool. C. Elementary, like how patronizing, right? Elementary consequences of Lagrange's theorem. Any
We are Watson
comments?
now.
Any comments on C? Like, I'm not okay. Let
Hmm.
me clarify something. I don't know if I would have an easy time solving most of these exercises, to be honest. But to me, it's more about, like, again, to me, it's more about the intuition. If I have enough time, I probably can figure this out. But I'm not really pushing for it.
Uh, Can I just say that C3 is actually kind of silly?
Let G have order 4. Either G is cyclic or every element of G is its own inverse. Conclude that every group of order 4 is abelian. Can you elaborate?
Like, it's kind of silly because just because you happen to have order 4, you are forced into being commutative. I don't know, that's funny to me for some reason.
No, but let's go there. Why order 4 means commutativity?
Uh, why order 4 means commutativity? Well, in this case, it's because the only prime factor of 4 is 2. Um, so you're kind of forced into the situation where
Wait,
uh,
the order of the you said what is true?
the only prime factor of 4 is 2,
Ah, oh
right?
yeah, that is true.
Um, so like, okay, suppose you have 4 elements, and let's just label them like 0 to 3 for the sake of our sanity.
Sure.
Um, okay, so G has order 4,
Let's say that
and the
they are
claim
not
is,
modulo, because being modulo is cyclic already, right?
yeah, okay, so the claim is it's either cyclic or every element is its own inverse. Um, the cyclic case is like, okay, that's clearly abelian already, so that's, oh, it's just integer addition, right? We know that's commutative.
Yes.
The case where every element is its own inverse is like, okay, and that means, in fact, that
Well, let's just start by
instead of
asking why there's no third option.
why there's no third option, because G has order 4, right?
Yes.
Which means in order to make a subgroup of that, there's the empty case where you just have one element that's not interesting. You have the case with 2 elements where you have the identity and something else, and then that something
Yes.
else must be its own inverse no matter what.
Yes.
And that's clearly abelian, right?
Uh,
Um,
yes, because the other element is the inverse of yourself.
but then that means if you consider the cosets of that, you have, well, you have 2 of them because your subgroup has order 2. So in order to get to order 4, you need a second one, right?
Yes.
Um, but that implies that the, well, if you just, there are basically, well, you have 4 options, right, to make a coset. The the simple option, or rather the non-interesting option, is if you pick the identity or the element that's already in the subgroup as to build the coset, and that just gives you the same group, the same subgroup. Or you can pick an element that's not in there, and then what happens? Let's say, for the sake of argument, that you.
Okay, let me try to help you on this. You can only have 3 options because you either have a subgroup with 1 element, a subgroup with 2 elements, or a subgroup with 4. And that counts
Yes,
to
and
4 possibilities because it's 1, 2, 2, 4, right?
yes.
In 3 of these 4 cases, in order for it to be a subgroup, you either are the identity element or you are yourself in your own inverse.
Well,
So 1,
actually,
2,
let's
2 is done, right?
1, 2, 2 is done.
Yeah, you have the subgroup with 1 element, order 1, one subgroup of order 2, and another subgroup with order 2. In all of these 3 cases, you are either identity or this is true, right?
Uh, yes.
Then the only case that you have to prove now is the case with 4 elements as the subgroup, in which case H is equal to G.
Yes, and that means that if age is equal to g, then if age is equal to g, then that means there are there's only one coset possibly, right?
Yes. But why does that need to be cyclic then?
Uh, why does it need to be cyclic? Because why does it need to be cyclic? Hmm, that's a good question actually. The way I see it, and maybe this is jumping ahead a little bit, there are like two different ways you can construct this group of order 4. You can either use integers modulo 4, and that's clearly cyclic, or you can use a pair where each element is a boolean, basically.
With its own inverse, right?
Yes, and the addition of the pairs, well, it's not really. The addition of the pairs is basically XOR, so each value is its own inverse. So
Hmm. Is a multiple order. Hmm. Yeah, but we cannot use theorem 4 for that, right? Because G order is 4, and 4 is not prime. So we cannot just say the G, because this would help us just do the nail in the coffin for that. Yeah, I don't have a clear intuition on why G needs to be cyclic in that case. In the case that the subgroup is 4, the order of the subgroup H is 4. But yeah, this makes sense, and these make sense. Right? If both of these things are true, uh, wait, I think we don't have to prove it, right? This is just being stated. We have to prove that they are abelian, which is kind of trivial if you think about it.
well, the cyclic case is clearly abelian because it needs to
No,
be
of course it
isomorphic
is.
to mod 4.
Yeah, of course
And
it
the
is.
other case is you have a pair of mod 2 integers, which is isomorphic to booleans.
Yeah, okay, so we were just complicating this thing. It was educational, but we already had the answer for this portion, and you were discussing the premise. So, great stuff.
Well, it's a good premise to discuss, regardless.
Yeah, I agree. Okay, any other comments on C? Or can we move on? Instead
Uh,
of saying known elementary consequences, it's further elementary consequences.
yeah, I don't have any more comments on C.
Okay, cool. So D. So this is talking about the indexes of things. So we have let G be a finite group and let H and K be subgroups of G. Prove the following. Um, suppose that H is contained in K, and therefore H is a subgroup of K. So there is like a nesting. Then
Yep.
we say that the index, we should divide the order of G by the order of H. This is equal to dividing the order of G to the K, and then K to the G. No, K to the H, sorry. Why is that the case? Why is that the case? I mean, stating as division makes this trivial, right? But I shouldn't do that. Because this is essentially saying there is a number divided by k. multiplying by k divided by another number. If you cut both numbers, the both k's, you get this. Oh my God, obvious. But I think we should use the fact that H is a subgroup of K.
Well, yes. If H is a subgroup of K, then the theorem applies to that pair of groups. So H must be a divisor of, well, the order of H must be a divisor of the order of K in that case, right?
The order of H must be, repeat that please?
It must be a divisor of the order of K, since H is a subgroup of K, clearly, right?
Okay, so let's say that the order of this is n. What you're saying that this must be a divisor of n. Or
Yes.
yeah, but how are you gonna go from these to this though? Then
Well, if H divides K in n pieces and K divides G in m pieces, then it is easy to see that G H divides G in n m pieces.
wait, could you repeat that? You're saying that this
Uh,
is that K divides
if H
G.
divides K in n pieces and K divides G in m pieces, then it is easy to see that H divides G in m pieces.
M or N you said.
Nm, as
N.
in n times m, because
Oh yeah, that is
uh,
true. No, that is true. That is true. Is that enough to say that we done D1? I like my solution better. This is just fractions, and that's it.
who would have thought that the rational numbers are so useful?
Well, they always were. The order of the intersection of h and k is a common divisor of the order of h and the order of k. Um, Wait, so you have two subgroups. There's no relationship between them in this case. And you have two subgroups. And the order, you were asking the order of the intersection. And it is the common divisor of the order of h and the order of k. Is that true? Well, given that it is asking us to prove it, it's probably true.
Well, that intersection must be a subgroup of both H and K, right?
Yes.
That means that the intersection, if you uh, the order of the intersection needs to be like it directly follows from the theorem because that's a subgroup of this intersect, or rather, the intersection is a subgroup of H, so it must divide H, and it's also a subgroup of
Ah,
K,
that
so
is
it
why.
must.
Okay, that is the way you explain it. It's because the intersection is a subgroup of both, and because of the theorem, that means that it must be a common divisor of both, which means this in English.
Yeah.
Okay, that's I'm satisfied with that. Any other comments on D, people?
We have a bunch of things about prime numbers afterwards. Again, number theory. For some reason, it keeps showing up everywhere.
No. I said that during the explanation. Everywhere that we go, at the point that we have stuff to talk that regards the number of elements in things, I think we are fucked from that point onwards because having the number of elements matter means that if they are prime, they probably matter. It's the least common divisor, it's the least common denominator in things. All of those things apply apparently. So I think at the point that the number of anything matters, we are done. It's written. It's the number of anything. Number theory. That's like okay.
Yeah, but yeah, I don't have any more comments on D.
Okay. E. So E is divided in two kind of, well, two portions. So first, more exercises on cosets. So let G be a group and H a subgroup of G. In a standard setup, let A and B denote elements of G. Prove the following. If they are the same, that means that this is there. And I think you can use the proofs that we use to prove the um, if A is an HB, then they are the same. You probably can use that fact in here to prove E1. Um,
Mm,
yes, Mani?
yeah, no, I was just thinking about um, if there's any trick you can do with the fact that you have a B inverse to
Well, of
prove
course
this a
you.
different way.
Well, of course you can. You can cheat, like what I like to do. I just see that okay, grab this B, pass to the other guy, inverse, cut the H's on both sides. Done. But that's not how you do that. Like, I'm not recommending that. This is not mathematical advice. Search for
Uh,
professional.
well, actually, yeah, no, actually, there's a very straightforward way to prove this. If just using the fact that you have a B inverse on the right, right? Uh, if A B inverse is in age, then A is clearly in age B, right? Because A B inverse B is just equal to A.
Wait,
But we
repeat
know
that?
that A
No, 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 no.
must,
Wait. Repeat that.
like, okay, if A B inverse is inside of age, then clearly A is inside of age B because A B inverse is in age. So if you multiply that by B to make age B, you just get A at that point, right? So
Yeah.
A is clearly in age B. And A is also clearly in age A because if you instantiate the elements of age to be the identity element, then EA is just A, right?
Yes.
So that's one direction. The other direction is a bit trickier because then you have to prove that, okay, if A B inverse is in, if the two sets are equal, then A B inverse must be in age. I'm not entirely sure how I would go about it, but it's probably not too different from what we already did.
Yeah, I think it's related to the proof of the if A is in HB, then HA equals to HB. That particular step from the beginning. I think that is where you do some like different manipulation to get this ongoing. So it's yeah, this thing. I think you would use. I imagine you would use this somehow because this is where we are like saying we
Yeah,
are doing the
yeah.
manipulation. So I expect it to be similar to this. Anyway, so any more comments on? Oh, actually, yeah, let's go back. Yeah, any more comments on E before we go to Theorem 5?
Not really.
Okay. So Theorem 5, which is the other way around, a useful converse. Um, how do you pronounce this name? Cauchy's?
Cauchy, I think.
Cauchy's theorem. If G is a finite group and P is a prime divisor of, I don't remember this syntax anymore. What does this mean again?
That's the order of G.
Okay, so and P is a prime divisor of the order of G, then G has an element of order P. Again, wild shit. For example, a group of order 30 must have elements of orders 2, 3, and 5. Cauchy's theorem has an elementary proof, which you can found way later. In the next in the next few exercise sets, we will observe all possible groups whose order is less or equal to 10. By theorem 4 of this chapter, if G is a group with a prime number P of elements, then we
Not
can
approximate.
approximate
It's an isomorphism.
isomorphism.
There's an
Sorry,
isomorphism. Yeah.
it's an isomorphic to modulo. This takes care of all groups of orders 2, 3, 5, and 7. In exercise G6 of chapter 15, it will be shown that if G is a group with p square elements, then G is isomorphic to modulo of the square, or the Cartesian product of the modulus separately. This will take care of all groups of orders 4 and 9. The remaining cases are examined in the next three exercises sets. So let's just recap what this means, right? Because I know you guys are very smart, but I'm stupid, so I like to recap stuff. So this means that how can I say this? The order of the group G dictates the presence of elements whose order are the divisors of the group order. So that's why it's saying here this. A group of order 30, which is the bigger group, must have elements. And again, definition of an order of an element is how many times you can apply the function with the element itself to get to identity. So essentially, how many times you have to apply f to cycle with the element itself. So in case of order 30, we know ahead of time, just by the order, that there must be an element of, or at least one with order 2, at least one with 3, and at least one with 5, sorry. And those apply for the prime numbers, right?
Yep.
Which again, wild stuff. Okay, so next is the 6 element groups, so F. Does anybody have F comments, I think?
Press F to pay respects.
Yeah.
I actually spent some time thinking on this one. F1 is pretty interesting, actually.
Prove that BA cannot be equal to either E, A, B, or B square. Cannot be. How do you prove that something cannot be? You just say it is and you see if there's nonsensical shit?
Yeah, I went through all of those 4, and in all cases, if you impose that equality, you end up with a group that actually has less than 6 elements.
Well, isn't that kind of obvious? Because doing equality means removing one of those, like removing one of the 6 to be something else?
Well, not necessarily, because BA is not in that list, you see.
Ah, BA is not here. How did you do that exercise then? How did you go to that conclusion?
I just went case by case. Like the 3 first ones are pretty easy because if BA equals E, that would imply that A is an inverse of B. But we already know that A is E inverse to itself, and each element has only one inverse. So that forces A to be equal to B. And that means you actually have.
Wait, you know that A is the inverse of itself how?
Because by the theorem, here, like at the beginning of this section, it says, okay, by Cauchy's theorem, G has an element A of order 2. So because A has order 2, that means A is its own inverse.
Wait, I thought U being your own inverse means that you have order 1.
No, only the identity has order 1.
But isn't the order how many times you're going to apply the function?
The order is how many instances of the element you have.
Ah,
The
so
number of
it's not how many f applies, it's how many arguments to f.
Yeah, the number of applications of F is 1 less than that.
Okay, so I got it wrong. Okay, no, then it makes sense everything that you said. I follow.
Yeah, like if BA is equal to E, then that means A and B are inverses, but we know that A is its own inverse, so that forces A to be equal to B, which makes us end up with just 2 elements. So clearly that cannot be the case, right?
It forces us to only have 2 elements, and the reason for that is because these can just be derived from these 2 then?
No, it's because then we know BA is identity. That means B must be the inverse of A, but
Yes.
A is the inverse of A, so A must be equal to B.
Yes.
which means that the elements collapse to E, which is the identity, A,
A,
and then B, which is just equal to A, so that's not a new element. B
yes,
squared is just the identity because B is equal to A and A is its own inverse, right?
yes,
AB is also the identity because B is equal to A and A is its own inverse, right?
yes, yes.
And AB squared is just A.
Also yes. Yeah, no, that makes complete sense. So you have to do that type of exercise 4 times,
Yes.
and you're gonna get to conclusions like, okay, that goes against the premises, that's wrong, blah blah blah. And
Yeah.
what about this second portion?
Those are the cases where if you impose that equality, you actually don't collapse any elements. You still have 6 at the end.
But why those? Why AB and AB square?
Well, if you look at the two next ones,
It's because those are the elements. You don't have any other options. I see.
yeah,
Yeah, no, makes complete sense. Okay, any more comments on F?
F is the first letter of fun.
Sure. Sure, 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 sure. Okay, G. I guess this is gonna be kind of similar in terms of mechanical process to F. Am I wrong?
It is kind of similar, yes. It's a bit more involved because the group is larger, right? So you have more details to keep track of, but
Yeah,
it's
but it's just
essentially the
more.
same.
Yeah, but I wouldn't say that it is essentially different. It is essentially the same, but just more laborious.
Yeah.
Okay, any comments on G before we move on? Okay.
Not really.
Okay, F, which is the server of 8 element groups. Why? Okay, and just to recap, we are doing this because allegedly, um, well, not allegedly, by theorem 4, the primes are taken care of. So true 3, 5, and 7. In a future chapter, 2 chapters from now, we're going to see that the squares are done. So 4 and 9 is done. What does it remain? 6, 8, and 10. For whatever reason, 10 comes first before 8. Don't ask me
It's because
why.
act- it's because 8 is actually more interesting. It has more cases.
Okay. But this is what we're doing. The exercises are for the remaining people, right? So 6, 8, 8 and 10. Remaining in terms of 10, counting to 10. Okay, so H. It is okay. So we're talking about modulo 8. Let us assume now that G has now no element over the 8. Hence, all the elements are different in E, and G have in G have order 2 or 4. And why that's the case? Because of the, how should I say?
Well, 2 is a prime factor of 8. And in fact,
Yes.
4 is also a factor of 8, and its only prime factor is 2. So you kind of. That's kind of the only option you have, really. Oh, those are the two only options, I should say.
Yeah, but this is a little bit um, this is a little bit annoying to me because 8 is not a prime, right? Well, I shouldn't say that. 8 is a number. We can only talk about its primes in terms of the order of the elements because that's what what? Cauchy.
Okay.
Cauchy's.
That's what Cauchy's theorem states. You can talk about the prime orders of elements given the group order. 4 is not one of those. So,
But it's 2 times 2, so
sure, the theorem doesn't state anything about that. Like this could have said something. I don't know. Why is 6 not in here? Right? It's probably gonna have a
Well,
6, but it's not in here because it's not a prime. So why is the 4 here with no explanation? I think that the exercise is just assuming you're gonna get that.
well, if you think about it from another perspective. The Suppose you have an element that has order 4, right?
Yeah.
Clearly, the square of the element has order 2, right?
The square of the element has order true. Hmm. Wait, why is that?
Well,
You should apply
because
the elements to itself.
yes, if you treat that clearly, the result of that clearly must be another element in the group, right?
Yes.
That element has order 2, which is a prime factor of 8, you see?
Hmm. Hmm. I see. I see. I see. I see. I see. I see. So the exercise that if you have a group of order 4, no, an element of order 4, and you square that element, the outcome of that is an element of order true.
Yeah.
Yes, 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 that makes sense. I am confusing order of elements with order of groups. That's why it was taking a while to me. No, but it makes sense. It actually does make sense. Okay, so any comments on H, people?
Um, I like the fact that quaternions show up here again, actually.
Again. Yeah. Which exercise they show up? 4?
7, actually.
7. The equations a to the 4 equals to b to the 4 equals to e, a square equals to b square, and ba equals to a to the third b completely determine the table of G. Write this table. G is known as the quaternion group Q. Thus, the only groups of order 8 up to isomorphism are modulo 8, triplets of pairs, and pairs of uh, fourtlets. Is that how you say that?
Well, it's not really because one side of the pair has is modulo 4 and the other is modulo 2.
Oh, it's modulo. Okay, so it's triplets of modulo true, pairs of modulo 4, modulo true, D4, and I forgot what that is, and quaternions.
D4 is the dihedral group of uh, of quadrilateral. That's the group of symmetries of a square, if I'm not mistaken.
It's been a while since we talked about that.
Yeah, but it's back.
Um, okay. So is this any different from the sixth case or 10th case, like in terms of mechanical labor?
Well, clearly there are more details because for some reason groups of order 8 you have more options than groups of order 10. But yeah,
Yeah,
no,
but
mechanically
no, but
this
it,
is
it's
just
more it's
more
more
of the
obvious
same.
because you can describe 8 in different forms, right? This is essentially powers. So 2 to the power of 3 is 8. This is multiplication. Are
Actually,
squares.
actually, I think I have an intuitive reason why. It's because groups of order 6, 6 is a product of two primes, right?
Yes.
10 is also a product of two primes. So
Yes.
they kind of have the same number of alternatives, right? But 8 is actually a product of three primes. It's 2 times 2 times 2.
Yes, yes, that is related to what I was saying. There are more ways to describe 8 than there are ways of describing uh, 6 and 10. Um, well, assuming the description is going to be either modulo or Cartesian and things like that. Okay, aside from that, any other comments in H before we move on?
Quaternions are cool.
Well, they are cool, but usually, again, in programming, you only usually see them in game programming, right? And probably math programming, but We seen those when we were making Lyceum.
Yeah, turns out they're really important for three-dimensional rotations.
But not only that, right? If you have any object moving and you have a notion of a time in your game, you're gonna use quaternions, right?
Uh, I
I
mean,
mean,
you
that's
could,
how I see it.
you could, but not necessarily.
What do you mean?
Like, if it's a 2D game, you're probably not gonna use quaternions ever.
No, but then you're gonna use the triplet if the game is in 2D with time. With time, no, there's a notion of you calculating something based on time.
No, actually, because here's the thing: use quaternions for the spatial coordinates. In particular, you need them for three-dimensional rotations, but that kind of forces you to use them for um, points. But then you have real parts of equal to zero most of the time.
Yeah, but
Uh,
that's not related to what I'm saying though. What I'm talking about is more about what each vector represents. So in the case of the first time I thought about this is when I was doing calculating the flow of like trying to doing the math to understand how much power in hydroelectric like um, what do you say
Power
uh,
plants.
power plant, yes, how much power that generates, and then you have the notion of a volume of water, but you need to include time on the math. So you have to have four vectors, three for dimensional stuff and one for the time.
Uh, that's not really the structure of a quaternion, though.
Oh, but can't you use, because those are just vectors, aren't they? These things.
No, a quaternion is a 3D vector plus a scalar, actually.
Oh, okay. So those are not just like four vectors glued together.
No.
I see. I thought they were. Interesting. Why
I
didn't you
am just.
save? Okay, go on, Tiv.
Oh, I was just going to note that you don't need to use quaternions for rotation. You can also use rotation matrices, and for instance, that's what the Sega Saturn uses on the processor it has to do graphics.
Yeah, yeah. When we did the Tetris stuff, we did rotation using rotation matrices as well. That's very old though. Like I think that was like way like 2022 or 3 maybe, beginning of 2023 maybe. We did a common Lisp Tetris game, and I wanted to use the matrices to rotate the pieces. Everybody was against me, but I won. Why do you have to have a new name for three vectors and a scalar? That seems unnecessary.
because like this is a little tidbit of history. Actually, quaternions predate the idea of using like vectors on their own, actually, by a little bit, because at the time Hamilton was trying to figure out, okay, how do you make a coordinate system to deal with like three-dimensional rotations in a way that is actually coherent, right? And
Oh,
a lot of people at the time were trying to figure out a system where you had three coefficients, right? And the legend goes that he was walking down a bridge, and then he had a flash of insight, and he figured out, wait, if I use a four coefficients and I have this identity, which he carved out into the bridge for some reason, then the math works out, and that's why it has. That's why a quaternion has four components, basically.
okay. Uh, cool. Okay, so eye exercises. So we've seen this before, the sandwich, the sandwich. But now there's more nomenclature to remember. So if okay, so if A is in G, a conjugate of A is any element of the form this, where X is in G. That's such a weird notion of a conjugate. I have in my head so fucking hard that a conjugate is um, like a mirror. Uh, I don't have that intuition. Whatever this with this, whatever this is. So yeah, and then it talk. Yeah, this is where we talk about equivalent. This is where we do the glue with equivalence relations, isn't it? Or is it the J one? Maybe it is the J one. But oh yeah, this relation tilde partitions any groups G into classes called conjugacy classes, which can be written this way. For any element A in G, the centralized of A, denoted by this, is a set of all the elements in G which commute with A.
Actually, backtrack a little bit. I think I1 is pretty interesting, where you actually have to prove that the is equal to a conjugate of is actually an equivalence relation. I think that's an interesting exercise.
Okay, so to prove that, it needs to be symmetric, transitive, and reflexive? I don't remember.
Yes.
Okay, so reflexive means that you can swap them around, right? The You can say that B is equal to the conjugate of A or something.
Yes.
Can we say that?
We can, and there's actually a neat trick you can do actually. Um, you can exploit the fact that x and its inverse are both clearly in G, right? So you can use the conjugate of x inverse to rewrite the conjugate into a form where, like, if x is equal to the conjugate of to a conjugate of b, that means a is equal to x b x inverse,
X
right?
inverse, yes.
But then to say the converse, to say that b is equal to a conjugate of a, you can exploit the fact that a equals is you can, like, you have the first direction, right, where
Yeah,
a
A
equals.
equals X, B, X inverse.
Yes, but then you can say, okay, what about b, um, like, you can, how can I say this? You can basically say, okay, what about b is a conjugate of is equal to a conjugate of a? You can say, okay, you can write it in such a way that you have, well, you know from going the other direction that b is x a inverse x a x inverse, but you can
No,
say,
no.
okay,
It's the other way around, buddy. You know that A equals to X, B, X inverse, and now you need to prove that B is equal to X, A, X inverse, right?
uh,
Maybe, yeah, I can write this down. Let me pick the tablet here.
okay, let's do that.
Uh, Let me pick the tablet. There we go. I think I should be ready. Yeah, this should work. So we know that A is equal to X. That's not how you write that. Uh, X, B, X inverse. This is given. And now we need to want to talk about this, right?
um, Mind you, those two x's are not necessarily equal, but it's convenient. um,
Yeah, let's actually write that down. They may be different. I'm gonna write them as y's. So y. So now what?
um, okay, here's the trick. You can pick y to be x inverse, actually.
I just had to sneeze. Sorry. Continue.
Yeah, you can pick y to be x inverse, right? And then you can put
Wait, why?
the
How? Why can you do that?
because the equivalence relation is that one is the left hand side is equal to a conjugate of the right hand side, not necessarily a particular one, right?
No, but you have to prove that. We don't know if it is an equivalence relation. Like we cannot use consequences of it being an equivalence
No, no, no,
relation.
no. I'm not using a consequence. I'm using part of the definition. The relation is A is equal to a conjugate of B for some A and B, right? And we
Yes.
want to establish that this is symmetric, right?
Yes.
So let's assume for a second that the equation on top holds, okay? That A is in fact equal to a conjugate of B, and we want to prove the converse from that.
We want to say this.
Um, yeah,
Because
sure, that works.
we can choose whatever x and y are, right?
Uh, sure, that works. Basically, the idea is you pick x to be equal to the y inverse, or vice versa. It doesn't really matter either way.
Mm-hmm.
And then basically, in order to prove that this is symmetric, you need to substitute one equation into the other, and it must still be an equation, right? You must not have a contradiction.
Okay, so you want me to replace the a in the second equation, for example?
Yeah.
Okay, so b is equal to y, y inverse b, y inverse inverse, right?
Actually, it would be not y inverse inverse. It would be y inverse and then y.
I am extremely confused. So you said y inverse. Why that would be the case?
No, look, it's you're substituting the variable in the middle, right? Which is a.
Ah, no, you're right. So I'm missing that I'm replacing on the second equation. So yeah, this is true. What are we gonna do about the x inverse though?
Well, x inverse is clearly y, right? Because if you substitute x with y inverse, which is what we picked, it's y inverse inverse, which is just y.
Okay, so it's gonna be y inverse. Blamma, blamma. Damn, boys.
Yeah, basically, if you assume, or rather, if you take as a given that a is equal to a conjugate of b, you can get the converse by picking your variable so that it becomes tautological, and that establishes that this is symmetric, right?
Okay, but okay, what about being reflexive and the transitivity?
Let's do reflexive first because that's trivial. If you just pick x equals identity, then well, clearly a is equal to a conjugate of a if you if you put identity and identity inverse around it.
Where did we talk about that? Um, reflexive. Oh, x is to itself for every a. So
Yeah,
is x conjugate to itself? Well, if you pick the bread to be identity, yes, right?
yeah.
That's such a weird way to talk about it. But the book introduced the notion of a sandwich, so that's on them. And then you have transitive, right? So if you know that x is the conjugate of y and y is the conjugate of z, can we say that x is the conjugate of z?
Is equal to a conjugate of z. Yes, it's just kind of similar to what we did for symmetry. It's just more substitution, basically.
More substitution. Okay. Any other comments on I?
Not really.
Okay. Okay, so J, right? So J. Group acting on a set. Let A be a set and then G be any subgroup of SA. G is a group of permutations of A. We say it is a group acting on a set A. What is SA again?
It's the symmetric group of A. That is, it's the group of all permutations of A.
But A is a set. What permutations are we talking about?
Permutation is basically an automorphism in this context.
Oh, okay then. Assume here that G is a finite group. If you pick a U in A, the orbit of U, more names, is this set. So GU, in which G is in, well, G is in G. So G is a function, right? That's why you were talking about permutations before.
Yes.
Okay. Okay. So any comments on J?
Uh, Not really.
Okay.
Devo, do you have any comments?
On J.
Not really, no.
Okay, and then finally K. I expect you guys to have comments on K. Because here's my understanding. Are we saying that you can use cosets to understand what to decode in a way?
Yeah, if you want to do like error correction, right, on a code, this is one way to do it, basically.
Oh, but it is using the notion of a distance. Thus, the
Yeah.
decoder receives a word X is to find a code word A such that the weight is minimum. Now, the coset C plus X consists of all the sums as C ranges over the code words. So by the previous sentence, if A plus X is the word of a minimum weight in the coset, then A is the word to which X must be decoded. A is the word to which X must be decoded. What is A and what is X in this context? I forgot.
Well, in this case, X is an arbitrary binary word,
Which is what we want to decode, I guess.
which is not necessarily part of the subgroup that we care about, but it's what we want to decode. Yes.
Uh-huh.
Uh, the subgroup in this case is all the codes that are actually valid, and we want to be able to go from one to the other.
No, so A is a candidate.
X is a candidate, and A is the decoding that you actually want to get from X.
No, no, A is the candidate because we don't know if A is the best one. That's why we are using distance to find what is the best A for it.
I guess that's one way to look at it. Yes.
Now, A equals to A plus X, so A is found by adding X to the word of minimum weight in the coset. Where is this coming from?
To the code received words, find the code words such that the weight is minimum. And then the coset C plus X. All the sums as C ranges over all the code words. So basically, um, if A plus X is the word of minimum weight in the coset, then A is the word to which X must be decoded. Basically, A would be the word closest to the identity, I suppose. Is that it?
Isn't plus XOR in this group? So X plus
Plus
X is identity? I
plus
don't
is XOR,
remember.
yes.
Yes.
Ah, plus is XOR. Okay, that answers it. So A is found by adding X to the word of minimum weight in the coset to recapitulate. In order to decode the received word X, you examine the coset, find the word of minimum weight in the coset, it's called the coset leader, and add E to X. Then E plus X is the code word closest to X, and hence the word is to which X must be decoded. Yeah, this is a very weird way to look at it though. Like, we are using cosets. What is the gain of using cosets in this case?
Hmm.
Ah, I know why. It's because you are fixing something and changing over all the elements of the subgroup. So if you have the group of binary stuff, you have the subgroup of valid code, and then you are ranging over all of the elements of that subgroup, but you are fixing the X because that is the what you want to decode at the end of the day. So this is just we're using cosets for encoding the problem, really.
Yeah, it's very unusual way to go about it, but it works, I guess.
Um, okay, then we have the list of exercises. Any comments on K?
I like the fact that it introduces syndrome as a mathematical term.
Yeah, that is weird, right? What are we doing? If X is any word, Hx is called the syndrome of X. It follows from part 3 that all the words in the same coset have the same syndrome. All the words in the same coset have the same syndrome. But that is the coset of the thing that needs to be decoded, right? Everything that needs to be decoded, an arbitrary binary string, that has its own coset every time.
Yeah.
And we are calling that coset a syndrome of X. And words in different cosets have different of course, this is obvious. The syndrome of a word X is denoted by this syntax. What is the need of this word?
I have no idea why they picked this word, to
Like,
be
why
honest.
can't we say coset of X?
Wow, that's overloading, but the word they picked to fix that overloading is kind of weird.
This is weird. Are we using coset off already? Because you said it's overloading. Have we introduced the notion of a coset off? Oh, yes. Because there is the coset of the subgroup, and I would be introducing the coset of the fixed thing
Of the elements you're using to
to
yeah.
fix from the outer G group. Yeah, I think okay. In that case, I'm against what I said. I don't like overloading in math because there's a lot of context, a lot of situations where all many meanings are possible because of the overloading. Uh, okay, that is very weird. Let the code C have Q cosets and let the coset leaders be. So what is the notion of a coset leader again? That is the one that
Uh
is the best candidate. Okay.
Yeah.
Explain why the following is true. To decode the received word X, compare the leader, the syndromes, um, with with syndrome of V1 and find the coset leader EI such that this is equal to that, then X must be decoded using that. There's definitely an error of syntax in here that matters for understanding what this means. So is this
Yeah, it's
missing a
probably
parenthesis before the comma?
that's what I think. So yes.
Okay, what does it mean to say syndrome of the candidate? So syndrome of the candidate means the coset fixing on the candidate. And you're gonna choose the leader in which their syndromes are the same. Why that's the case?
Uh, because in some sense, the leader is like, well, if you go back to the definition of how you do this decoding, right? The leader is like it's kind of similar to the identity element, but not it's not really an identity element, right?
No, it's
Well,
about
it would
minimum
be,
weight. It's about being the best one to decode X2.
yeah, basically it's the closest element to identity in
In
that
that
call
code
set.
set. Yeah. Well, when you say closest to identity, what do you mean? Oh, distance zero. That's what you mean.
Yeah, because identity is because the identity would be zero in this case, right? And
Okay,
that
that would
has
mean
a weight
perfect
of,
decoding.
yeah,
Okay, I see what you mean. You sent something that I already have in the catalog. That is identity element. That's a very
yeah,
cool way to look at it. I never thought of that in those terms. Yeah, that's very cool. That's very cool. Okay, so the leaders are they are the closest ones to identity. I follow that. Then what?
yeah. Then you just pick the leader for the call set that X is in, basically.
Well, but what does it have to do with the syndromes being the same? That's kind of my drill. What you said is I understand, but that doesn't imply this equality as far as I can tell.
If the syndromes are the same, then that coset has the word you want to decode to plus X in because the syndrome of it is X.
I guess that is true. I guess that is true. Let's just recap for a little bit. Marinho said that if you have E equal to identity, that means that it is a perfect decoding because it's gonna be
You
X.
didn't,
You decode X to itself. You didn't have to approximate to anything else. You just got it.
yeah, basically there was no noise in the transmission. You got the message correctly. So you just add identity to it, and you get the same thing, and you're done.
Yeah, that is a very interesting way to look at it. Holy damn.
Yeah, in some sense, the call sets are classifying how much error there was in transmission.
Yeah. Yeah. I agree with that. Okay. Any more comments on K before we wrap this up? We're kind of over time, but this chapter has a bunch of exercises, so I'm letting it over time.
Not really.
And then finally, as Marinho already spoiled us before, we were two chapters away. Now we are one chapter away. So next time we're going to be talking about something more morphisms.
Yeah.
More morphisms. So I'm excited because I'm hoping somebody will be able to explain this in a way that I will be able to remember for the rest of my life. That's what I want really. That's what I want. Jesus. Okay, yeah, this one has a lot of exercises as well. Okay, I'm gonna finish the recording.